lots of collaborations between UK and UFL using the instrument, so John probably will give some examples.
Well, ladies and gentlemen, thank you very much. I realize it's getting late in the day, and if I don't speak for an entire half an hour, I'm sure that will endear me to you a little bit more. My name again is John Chaney. I'm the Associate Director of the Surface Chemistry Material Science Laboratory. It's the laboratory with the ever-changing name. My personal favorite is the Center for Chemical Epistemology, but that did not go over very well. But nevertheless, I'm going to be giving you an advertisement today for the kinds of tools and techniques we have available to the larger, in this case, catalytic community of Kentucky and the surrounding regions. It's useful to talk about what we are interested in doing. That is, we'd like to ask the question, what do we mean by surface science? What is it we're actually going for? To define that, though, I'd like to give you a working definition for a surface. And you find when you begin looking at these matters, it's a little harder than it first meets the eye. This is a formulation of a statement made by Irving Langmuir, which was recast by John Hudson from, and I'll mispronounce this, Rensselaer, how do you say that? I can never get that out of my mouth, but the school in New York, where we talk about a surface being created by any abrupt change in physical properties as a function of real space. What that means is a surface is the place where a material ceases to exist. And the pedagogical example I like to give, if I hold this object up, you all recognize it as a hand. This hand, though, is composed of blood and tissue and bone matter. You are seeing this hand at the place where it ceases to be a hand. That's a kind of a Kierkegaardian definition of surfaces. If I peel away the skin and show you the tissue underneath, I've simply exposed a new surface. I can go on ad infinitum, and all you will ever see is the fundamental point of contact between the material and the rest of the universe. So it's kind of a point of philosophy. Can you ever know anything real about the internal workings of a material? The conclusion one would take from that, if a surface is the place where you have fundamental physical contact with the rest of the universe, then we must say that that's the place where all chemistry happens. So now we're in a position to give a relatively bad definition of surface science, and that would be the study of all things chemical and physical. I want to limit our scope a little bit. Generally, when we talk about this, we're talking primarily about the gas phase, solid phase interaction, and that has bearing, of course, on the physics and chemistry of condensation, coatings, and, of course, catalysis. These kinds of studies, we try and isolate one chemical phenomena from the rest of the universe. That's the most unlike the real world conditions. However, if we want to know something precisely, we often have to create this artificial environment. So we try and work in very stringently clean environments with careful in situ control. So what do we do with surface science? I consider surface science a rather fundamental. I'm very fond of pre-Socratic philosophy. Here's a picture of Thales, who was a philosopher on the order of 500 BC. He's the earliest of the pre-Socratics. And the pre-Socratics were primarily concerned with what is the universe made of and how does the universe behave. Well, for solid materials, we're interested in asking similar questions, and you can see the similarity. We'd like to know what is the chemistry of a material, how does it interact with other materials, and then we would like to go beyond the Thalian natural philosophy, and we'd like to say how can we use these various chemical interactions and chemical changes to bring about some interesting chemical physical properties. If you're in the business of making OLEDs out of metal oxides, you might perhaps be very interested in a high work function material, and we would design some surface chemistry to accomplish that. If you're interested in catalysis, you might be interested in some particular reactivity with methane, for example. The kinds of questions that we're trying to answer are things like structure, bonding, work function, what are our various valence bands that can interact with other materials. And we have an interesting laundry list of tools that we use to try and answer those questions. A wide variety of spectroscopic techniques: OShea electron spectroscopy, energy loss spectroscopy, secondary electron energy loss spectroscopy, X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, low energy electron diffraction, et cetera, et cetera. And there's a variety of combinations and iterations of these. We'd also like to modify materials, and we can do that in a variety of ways through some physical treatment, through some thin layer deposition, through some gas phase reduction, oxidation chemistry. We can also modify things by ion bombardment and etching. Here's a little collage of the tools we have available. I'm not sure which is actually heavier. This tool is at least 20 pounds overweight right now. So this is the RHK-VG multi-lab system. I'll describe that in a little more detail in a bit. But you can see there's a lot of spectroscopic and a lot of microscopic tools to do a very thorough evaluation of the material. The applications are not just for catalysis, although since you're a catalysis group, I'd like to leave you with the impression that's all we're concerned about is doing catalysis work. But we can be pulled in other directions from time to time. Let's go on and take a look. To help you navigate the alphabet soup of spectroscopic techniques, I'd like to just go through this bit of a review. I don't mean to offend your intelligence. We've all had to study these sort of things, but the acronyms can get a little heavy. When we're talking about core level spectroscopy like X-ray photoelectron spectroscopy and ultraviolet photoelectron spectroscopy, I'll be skipping this. We're talking about knocking the secondary electron out of the core and analyzing that. Now you have a couple of phenomena that can happen when that atom relaxes. It can relax to give off a photon, and that's the EDX type of, that's what you would analyze in an EDX instrument. I'm not going to discuss that. The more interesting thing would be a further secondary electron being given birth to. That's the Auger electron, and that's Auger electron spectroscopy. I just mentioned that because I'm going to talk about the two techniques. The two techniques are looking at core secondary electrons, but can provide you with very different information. We can review the physics at a more convenient time. Now let me give you a little tour of the lab. The multi-lab system, which you saw some photos of in the collage, is a series of interconnected vacuum chambers capable of achieving ultra-high vacuum conditions on the order approaching 10 to the minus 11 torr. Now, the mean free path of a hydrogen molecule at that pressure is on the order of a couple 100,000 miles, so we're talking about a system which is a little bit cleaner than outer space near the Earth. So we have very stringent control. The heart of this system is a 150 millimeter radius hemispherical electron analyzer, which allows us to look at ultraviolet photoelectron effects, the X-ray photoelectron effect, and the Auger electron distribution from a material. We cause those events to happen by a variety of excitation sources. So those are our photoelectron techniques. Coupled with that, we have in vacuo tandem STM, which I'm told now in another 2 or 3 months that will be a dual AFM STM, so that with those two tools, we can do a very broad, thorough analysis of the chemical and physical aspects of the material. I'm not going to talk so much about the lead. We do have a lead, since that's really only amenable to single crystalline material. I'm going to just gloss over that. What is particularly of interest to the catalysis work that we do is we have available a high-pressure gas cell, which would allow us to take a catalytic material and expose it to a high temperature on the order of 500 to 600 degrees C pressure of hydrogen or oxygen or what have you, and we can go about as high as 20 bar without the operator becoming nervous. That type of gas can be pumped away, and you're right back into ultra-high vacuum without ever perturbing the sample. So in a very clean way, we can follow some reduction and oxidation chemistry of a catalysis substance. And I'll show you an example of that. Before I go on and start describing some of the examples, I do want to put a caveat here. Much of the work we've done is proprietary in nature, so I'll apologize now if I do not give you as much detail as you might like to see, but those of you who might be interested in doing business with us in the future will appreciate my reservation in saying too much on these matters. We do have room to grow, and we would like to add some additional techniques, and I'll describe that near the end of this presentation. Here's an example of X-ray photoelectron spectroscopy of a metal oxide. This is an indium oxide. Actually, that's interesting. I didn't get my borders, but this corruption actually makes it a little easier to read. This is binding energy of the photoelectron in the core level. And if we look at the survey spectrum, we see the lines for the 3D 3/2 and 3D 5/2 indium lines. This is carbon, and this is oxygen. As you know, metal oxides are reactive to a variety of species. Indium oxide has some particularly interesting reactivity with atmospheric carbon. It's very difficult to get rid of. Also, you have multiple states of oxygen on the surface. We do another experiment where we focus in on the oxygen information. Here I'm following this line in the back with the two features. What we discover is that oxygen resides on the surface of this indium oxide in at least 2 states, possibly 3. If we bombard this surface with an energetic ion to do some controlled damage of the surface, we see we remove 1 or 2 of those states, and we're left behind with a very narrow, unique form of oxide. So here we're actually exposing what we might call the bulk oxide. Although, again, remembering we've simply cut away a new surface. The carbon, on the other hand, while it's a relatively strong signal for carbon, with a little bit of ion interrogation, we're able to remove the carbon. What that tells us is that the reactivity towards this atmospheric carbon is very much localized to the surface. We don't have diffusion effects, as it were, through the bulk. We could say more about that, but let me describe another technique. This is, again, X-ray photoelectron spectroscopy of a catalyst which contains cobalt, among other things. And I won't go into that. But what is interesting, if we take the raw material, the line is a little noisy because the signals are weak and it requires some deconvolution from external software. This is the 2p 3/2 and this is the 2p 1/2. If I take this material and expose it to a high temperature, high pressure hydrogen environment, I can sequentially reduce it. And here we have a variety of temperature steps going all the way to 600. What's interesting is we have this cobalt feature gradually evolves into two new features, here and here at its maximum temperature scheme. What we see is the formation of a reduced cobalt form and some other kind of cobalt oxide, which I don't want to really get into the larger descriptions of, but it is interesting to note that these materials, as they are made, certainly can have a variety of forms, a variety of oxide forms, and if you have overlapping of those forms, it can be quite complex to try and ferret out the meaning and significance of those. So that's one thing that we can do, and that's, again, an example of this high temperature, high pressure exposure to hydrogen gas. Let's go back to one of my favorites. This is a OShea electron spectroscopy of a metal oxide. This is actually a tin-doped indium oxide. Generally, we present this sort of work as a differential intensity. That's simply because the raw intensities of the individual peaks are very, very weak. The OShea event is not a common event, and so we do the most we can with the few electrons we get. When you differentiate this, you see the indium OShea electrons appear as this ringing doublet, and generally we read the negative excursions of these differential plots. So we see a ringing doublet for the indium, we see a ringing triplet for oxygen. That's very common oxide structure, inorganic oxide structure. We see this very small feature here for carbon. Now all these other bits and bobs and peaks and wiggles, those are associated with deeper core transitions of indium. They are real, but the only major components we see in this is carbon, indium, tin, and oxygen. OShea is nice because it's particularly sensitive to the outermost layers, and it's particularly sensitive to the lighter elements. So carbon and oxygen are very amenable to a study with OShea. Now, what's interesting, if we focus in on the indium structure, and here's this same region, just sort of shown in a little more detail here, you still see the ringing doublet. That's indium in its that's indium oxide in its pure state. It's been warmed a little bit to drive the water off. You note that the peaks, this first singlet is a little bit shallower, is a little more shallow than the second one. The second negative excursion goes much deeper. That is important in identifying the oxide structure. If we do some hydrogen reduction, and here we've used deuterium, but for our cases we're just going to assume it's going to work the same as hydrogen. This material metallizes visibly. You go from a white transparent material to a very gray material, and you see an interesting change in the structure here. Again, the negative excursions here are almost the same, but this has shifted to the higher energy side quite a bit. Now all that's very important in saying something about the new valence structure of your indium in this material. And all these little dips and wiggles have particular, actually provide real information as to the atomic structure of that atom. Let's go on. Now, one of the things we like to do, this is surface analysis. Often we're interested, though, in scraping away these layers of tissue and exposing the, dinosaur bones that are underneath the surface. We can do that with energetic ion interrogation. Here's the case where we've taken some silicon, which has something in it, which is used for something, and I will answer no more questions with regard to that. But this is a catalytic process. We find that in this instance, you form a fairly thick oxide layer, which inhibits the catalytic activity of that something that has been impregnated into the silicon. This is actually This is actually a depth profile which was monitored via X-ray photoelectron spectroscopy, where we just simply followed those peaks. You convert the intensity into some atomic concentration, and away you go. With gradual scraping away of the surface with an ion gun, you can get an idea of the bulk structure of that material. Again, realizing that as you scrape things away, some things are a little easier to scrape away than others. It's just like breaking a foundation for a building. It's easy to take the dirt away, but once you hit bedrock, you have to expend a lot more effort. And so things like carbon and oxygen are removed quite easily, but if you have metallic species, heavy metallic species in this, you will have an enrichment of those. And in this case, you see a slight enrichment as you go along of this material, which I'm calling catalyst. Better not say too much. Let's go on. Let's look at another photoelectron technique. This is ultraviolet photoelectron spectroscopy. I've always been accustomed to just simply saying UPS, and that didn't become problematic until I moved to Louisville, and people thought I was talking about the shipping company. But this is ultraviolet photoelectron spectroscopy. This uses an incident beam on the order of 20.2 electron volts. Generally, we'll take a hydrogen gas and excite it to get the UV lines out. That allows us, because of the lower energy of the incident beam, that allows us to look more at valence structure rather than core level structure. We're still looking at a secondary electron emission, but from a much higher level. Now, for the lighter elements, the difference between a valence electron and a core electron is not that important. They essentially can be one and the same. Here's a silver oxide, wherein we've done some UPS. You can identify the Fermi level, and the Fermi level is buried way down in here. You can't see it. You actually have to do this experiment again at a much higher resolution. You can say something about the metallic versus semiconducting nature of a material, depending on how much density, how much electron density is localized near the Fermi edge. This spectrum actually has a lot of density relatively near the Fermi edge. Consequently, we would expect silver with a little bit of oxide on the surface to be largely metallic. As this material changes through either some surface modification or some further oxidation, we'd lose that density there. You can identify relatively easy things like work function. In my previous career, we were very interested in organic light-emitting diodes, and so this was a real workhorse in terms of identifying the work function of a modified substrate. You can go on. I spoke about changing the surface using an energetic ion beam. There's other ways that an ion beam can interact with a surface. Here's a case where we're actually doing something called ion scattering spectroscopy. This is not for the purpose of mapping a physical picture of the surface. Actually, Steve Overbury, we were chatting about earlier, is into that business. This is more for identifying species on the surface by their mass. We will take a low mass ion such as helium, but neon works also. We'll classically, elastically scatter that from the surface of whatever. And by looking at the energy losses of that classically scattered beam, you can relate the loss of energy there to the mass of individual atoms on the surface. So there's a mass loss, just like this is essentially a billiard ball experiment. Throwing a billiard ball against a wall, the trajectory and degree of bounce is a function of the mass of the wall. So you can identify the mass of specific surface atoms on a material. Now that's important if you had, say, a mixed palladium-platinum catalyst, and you'd like to know on the surface, of course, where all things chemical and physical transpire, you'd like to know how much palladium you have relative to platinum. This is an ideal way of getting that. Because of the nature of the surface layers, you begin to have inelastic phenomena happening the second layer below the surface. So this is only sensitive to the outermost skin of atoms on a material. That's actually quite an interesting technique. Let's look at something else, a little more physical. We're going to get away from the more chemical types of spectroscopy. This is a tool that we're just now bringing online, and we've had some very good success at following. Our first project with this has actually been to follow the alloying process of gallium droplets on a gold substrate using scanning tunneling microscopy. We get very good resolution of ideal materials. We get pretty good resolution of non-ideal materials. As I said earlier, we hope to upgrade this in a very small number of weeks to a dual AFM STM, so that we can have a full suite of microscopy tools in addition to our spectroscopic tools. I'm showing you just an example of a lead pattern. That's simply schematic, more just to show you it's something we can do. Where are we going? The Surface Materials Laboratory at the University of Louisville is a unique institution in this area. It's not to say it's the first time it's ever been created, and it's not to say that it's the best, that each individual technique is the best of its kind available, but when you build an ensemble of techniques, you make trade-offs. And this is a unique ensemble of techniques to do a full suite of surface chemical analyses. And right now, it's the only one that I know of which is available in a reasonable driving radius from your places of work to come and do this kind of analysis. And we are looking for long-term partnerships with our associates in industry and academia. We do have goals of expanding this system to sort of keep pace with demand. We would like to add some laser spectroscopy in the future. We would like to add tools for doing controlled film growth, metal film deposition, and we would like to, at some point, add some capability for mass spectrometry. SIMS, that's secondary ion mass spectrometry, is a much better way of depth profiling material than ion sputtering followed by photoelectron spectroscopy. Both are good. I'm not suggesting that one is bad, but SIMS is a much more accurate, precise technique than simple depth profiling. If you really need to know where the boron atoms are in your silicon wafer. But if you are interested in things like gross contamination in a material, that's relatively easy to accomplish. I'm going to end here. If you're interested in contacting us, I'll direct you to my associate in the laboratory, and I'll leave you my contact information as well. I'd be delighted to, as I said, take a check, or you can chat with me at your leisure, and I'll answer any questions that you have at this time.
Well, the floor is open for questions. We're getting to the tired mode now. So.
Yes, you had a question. I do this when I teach, so.
Yeah, I love it.
Yes, sir.
You say not all the work is done on catalysis. What is the primary use of the equipment at this time?
Well, actually, for the last few months, the primary work has been catalysis. but we do have, as I said, actually the project I alluded to was this alloy formation of gallium and gold, where we've taken sort of idealized gold substrates and followed the spreading of gallium droplets there. That's actually quite an interesting thing because I think the phase diagram of gold and gallium was put in the CRC handbook almost 30 years ago, and I haven't seen much. I haven't seen much beyond that. But we became interested in the gallium, of course, because it's used so commonly at U of L as a catalyst for a variety of things. And we were interested what happens as these gallium droplets spread. How do they interact with gold? It's kind of would be an interesting thing. What it would be the structural dynamics, perhaps, of forming that alloy. Other questions?
So the stem will be ready, the air stem combination will be ready in about 2 weeks?
2 months.
Oh, 2 months.
Yeah, don't burst out of the starting gate too early.
I heard 2, so.
Yeah, 2. You can insert 2 days, 2 weeks, 2 months, whatever unit you like, but 2 is the magic number. 2 months, that's not bad since we've been waiting for 2 years. So hopefully we won't go much beyond that. Other questions?
Yeah, if there are no other questions, then please help me thank John one more time.